Hello everyone. In this video, we will derive the equation for isothermal work. Isothermal work is the work done by an ideal gas under constant temperature. We will derive this equation in a step-by-step process, where each mathematical step is also explained in a physics point of view. Let us take a cylinder piston setup, in which an ideal gas is present. The temperature of the gas is T, the pressure of the gas is P1, and the volume of the gas is V1. If we increase the volume to V2, the pressure also changes to P2, but the temperature remains constant. We would need to find the work done by the piston in moving from volume V1 to volume V2. Let's get started. To find the total work done, we would need to find the work done for small volume changes and then add them up to get the total work done. But how do we find the work done for small volume changes? Well, we know that the definition of work is force times displacement, but we don't have the force and displacement of the piston directly. But we do have the terms pressure and change in volume delta V, which together give the same quantity of force times displacement. Hence, we get the small work done, delta W, as P times delta V. Now, all we have to do is add up all the small work done during the entire process where the piston moves from volume V1 to volume V2. But is it really that straightforward? We know that as the volume increases, pressure decreases, and as volume decreases, pressure increases. So, the pressure during the process continually changes, and to measure the value of the pressure directly at each position of the piston would be impossible. But we need the pressure at each piston position, and without it, we cannot find the total work done. In order to find the pressure at each position, we can use the ideal gas equation, which tells the relationship between pressure, volume, and temperature. We can notice that for a given temperature, T, the right-hand side is a constant, meaning that the information about every possible pressure and volume values are stored in the right-hand side constant. To find the pressure at any piston position, all we need to do is divide this constant by the volume at that position, and voila! We get the pressure at every position of the piston. Not so fast, if you haven't noticed already. We would need to find the value of the volumes at every single position now to get the pressures, which seems equally difficult. We can notice that at least there is only one variable, V, in the equation, rather than both pressure and volume as variables. Later on we will see how to get the individual values of volumes at each position easily. Let us first see what the sum of the work done due to small changes in volume from V1 to V2 looks like. We can notice that at each position, when the volume divides the term nRT, we get the pressure at that position, which when multiplied by delta V, it gives the small work done by the gas at that position, and hence by adding all the terms, we get the total work done. To solve the problem of getting the values of volume at each position, we would first need to take the nRT term out of the equation, since it is common to all the terms. Then, our sum can be written in the form of an integral, since an integral by definition is the sum for changes that are infinitesimally small. Hence, we get a standard integral, which is the log e, with the initial and final values v1 and v2 respectively, which only needs the initial and the final values of volume to give the required sum, without the need to manually measure the values of volumes at every single position. Since work done by the gas is the internal energy lost by the gas, we put a negative sign to represent that. There you have it, folks, an interesting and simple way to derive the equation for the total work done by an ideal gas in an isothermal process. If you like this video, then give it a thumbs up and share it with your friends, and don't forget to subscribe for more interesting concepts like these.